I'm the Marketing Communications Manager at Bruker Nano Berlin, Germany, and I will be your host for this event today. Welcome to the first webinar by Bruker this year, discussing combined electron backscatter diffraction and energy dispersive X-ray spectroscopy in the scanning electron microscope. Our speakers today, Dr. Lori Pallas and Dr. Daniel Gore, both of Bruker Nano, will present recent advances in EDS and EBSD integration and will show how both methods can be used together for fast phase identification. But before we start, I would just really like to talk you through some logistics. At this time, you should be seeing the first slide, the introduction slide of our presentation. To the right-hand side of your screen, you should also be seeing a Q&A section. At the bottom of this, we'll be able to type in your questions into a box and then click send. These questions will be then sent to us and will be answered by our speakers during the session. The presentation today will last for maybe 40 minutes, and after our speakers have finished, they will start answering your questions. If we should not be able to get to your questions during the live event, we will answer later by email. Also, I would like to point out that this web seminar is being recorded and will be able you'll be able to view it online from tomorrow onwards. Okay, so our speakers today are Dr. Lori Pallas, who is an application scientist here at Bruker Nano, and Dr. Daniel Goran, who also is an application scientist here. And I'll hand over to Daniel, who will begin. So Daniel, here you go.
Thank you, Stefan. Hello, everyone. We'll be presenting to the first part of this presentation, and then later on I will hand the microphone to my colleague Lori. So I will start with a few words about what we understand by an integrated EBSD/EDS system, and then I will pass to the main part of this presentation today will be about the advanced phase ID, this new feature we are releasing today. And before describing the advanced phase ID, I will have to, for those of you not knowing, I will have to present you how conventionally phase ID is done or was done until now. Then I will show you how this advanced phase ID feature works, and in the video you will see you will be presented advantages of using this new feature. And the most important thing system will have to have is a software platform. Integrated system will have to have is a software platform that controls both detectors, the EBSD detector and the EDS detector. And here on the left-hand side on the slide you have the EDS detector and the phosphor screen of the EBSD detector. And of course, this software platform will have to be able to perform all types of analysis possible, either standalone with one of the two techniques or with the two techniques combined. The software will have to have multiple features for viewing the results during the analysis, while they are acquired, but also to analyze the results and to interpret the results either online during the analysis or offline after measurement is done and we reload the data set. In terms of hardware features, at Bruker we have developed a few unique features to allow user to acquire data sets in optimized conditions. And one of these two are the tilting options for both detectors. So our detectors have this unique capability to tilt on around about an axis which is outside the SEM chamber, and this tilting option allows both detectors to follow the sample at basically any working distance inside the SEM chamber. And so the detectors follow the sample, and in this way you can acquire data sets in optimized conditions. When you have an integrated EBSD/EDS system, with the Bruker system, you can acquire in the same time EBSD information, acquire and analyze, of course, or and acquire and analyze a full EDS spectrum. What is specific to the Bruker EBSD and EDS system, integrated system, is that nowadays you can do this with pretty high speeds, depending, of course, on the type of detector you are using, and the type of detectors you are using, either EBSD or EDS detectors. The speed 520 points per second has been achieved using our high-speed detector, EBSD detector, and the quad X-flash EBS detector. And when we combine these two complementary techniques, there are a few advantages of combining these two complementary techniques. One of them is something that has been well known. It is well known in the field and has been done since the beginning for at least 15 years now, and that is to discriminate between phases creating similar patterns. And on the Bruker system, this can be done either online during the measurement or offline after when loading a saved map. And it's new, and we want to introduce to the field is the option to do phase ID online, either during the measurement or offline. Other advantage of combining the two techniques. So I'm going to start presenting you and now I'll present you the conventional phase ID and how this is done or usually done until now. First is basically the user chooses one particle in the field of view and brings there the beam in spot mode and acquires a spectrum. And based on the elements, major elements present in that spectrum, like in this particular case, iron, silicon, oxygen, and a little bit of magnesium, then the user searches in using a search engine in crystallographic databases for candidate phases. And for this particular chemistry here, searching in ICSD, in organic chemistry structure database, the search engine found 225 entries. And the next is the user will choose manually one of these entries and use it to try to index a pattern, Kikuchi pattern, corresponding to the same spot from where the EDS spectrum has been acquired. And if no solution is found or a very poor solution is found, then steps 3 and 4 have to be repeated until the right phase file or a phase file is found that gives a decent solution. And in this particular case, we have found this spectrum and pattern to fit to phaolite magnesium. So phaolite with a little bit of magnesium present. And of course, this is just the first 5 steps are to identify one phase. But if the sample contains more than one phase, then all steps above from 1 to 5 have to be repeated until all the phases have been identified. Then it's useless to set the more phases you have, the more time you will have to spend at the SEM before launching the measurement. And another thing is let's say, not so good, or another point that negative of the manual phase ID, the conventional phase ID, is that it not always gives the best results. And as you can see here, for this the red phase, the phyllite magnesium, this particular area of the map, grains are pretty well indexed, but grains in this part of the map here on the center of the map, that index may be, or sections were found for maybe just 20 or 25% of the points. This, to understand why this happens, I have to give you a few details about phyllite, what it is. I'm not a mineralogist, I'm a material scientist, but for those of you not knowing, phyllite is a iron-rich end member of the olivine family of minerals. That what's particular about these solid solution phases, that small variations of chemical composition can lead to a slight crystal structure change. And because of this, we end up with many phase file entries in the databases. And the probability to find the best phase file fitting these patterns, the patterns produced by this phase, in this particular case, is very low. The higher the number of entries, of course, the lower the probability. So this means that in this particular case, I chose a phase file which was very close, but not the best one from the database when I use the manual phase ID. And so, as I said, this conventional phase ID may not always give the best quality results. Here we have the map after doing the phase ID with the advanced, the new feature, the advanced phase ID. And you can see the phase, it's properly indexed all over the map, and all the grains are properly indexed, and we will see immediately how this is possible. Intermediate summary for the conventional phase ID, well, that it's manual, and then that means it's it can be extremely time consuming when you have many phases and unknown phases in your sample. It always gives the best quality results. And also must be done before launching the measurement, which means the SEM will be kept busy in the meantime. And if you have small particles or unexpected phases like precipitates in steels, or these phases can be missed unless they have a different gray scale in the BSE image, and then you identify them from the matrix, and then you go and manually identify them. Otherwise, you will just see at the end of the measurement that actually that area was not indexed, and it's a missing phase. Pass to the advanced phase ID. And before starting to explain how the advanced phase ID works and show results, I will have to give you a few details about the data set I'm about to show you. And here you have a BSE image mineral, and this, before starting to give any other details, I would like to thank Dr. Halfpenny and Dr. Michael Verral from CSIRO in Perth, Australia, for generously providing the data set. So this has been done in CSIRO in Perth, and they did simultaneous EBSD and EDS, using the high resolution EBSD detector in 10 by 10 binning mode, meaning the patterns used for indexing were having a resolution of 160 by 120 pixels, and they used our 30 square millimeter EDS detector. For this, they were actually not prioritizing the speed, but were prioritizing the quality, and they launched this in the evening, the measurement. So what they did, they used a 12 milliseconds export time and 3 frame averaging for the EBSD data, of course. And they acquired a pretty large map of 1000 by 750 points. And for the low magnification that they chose, because they wanted to cover a very large area, combined with the size of the map, that results in a pixel size or a step size of 1.66 microns. Now, this is the pattern quality map corresponding to the region of interest you saw in the slide before. And I'll now start explaining how the advanced phase ID feature works. The first step, it's pretty much it's very similar with what you saw before with the conventional phase ID. So basically, the user has to go in one spot and on one particle and acquire a spectrum and a pattern. And the same way, using the chemistry in the spectrum, the elements present in the spectrum, a search, it's done through a search engine in a database. And then in this particular case, for iron and oxygen, I found 289 entries. Then the band detection is done. This in the advanced phase ID feature, the band detection can be done in many ways, or you have more than one option that can be done automatically or in an interactive way with a smart band detection that we can discuss later on about it if you are interested, or manually, where the user has full access to the band detection, either deleting or moving or slightly changing the position of a band. And on the pattern, you see in red the detected bands, the band centers of the detected bands. And in step 4, which is actually the most important part of the phase ID, and the one that makes a difference or a big difference as compared to the conventional phase ID, is that the software automatically tries all 289 phases, and this happened in approximately 10 seconds. The result of that, of testing all these entries, the software will produce a list, a table with all the solutions found, and these solutions will be classified based on quality of fit. And quality of fit, we understand, or the quality of fit is given by 2 parameters. One is here on this column, and represents the number of detected bands of 12, which is maximum of bands that can be detected in this part of the software. So the number of detected bands fit 12 fitting the simulation, which means what you see here on top, these solutions have been found with 11 and 12 bands respectively. The second criterion is the mean band mismatch, and this is an average. It's the mean angular mismatch between the detected bands and the band centers in the detected bands and the simulated solution, the corresponding bands in the simulated solution. So what the user has to do is just to pick the best fitting phase file and drag it to the, or insert it to the phase list, and then the system is ready for acquiring data. And you would say, wait a minute, you just said that this is a multi-phase material, and then here you just identify one phase. That's true, but what you will see today is that with our system, you don't have to spend any more time at the SEM if you don't want to. You can launch the measurement just by knowing one phase to have, in a way, an idea of the quality of data you are acquiring. So it's good to have one phase present, and then you can launch the measurement if you launch a simultaneous EBSD and EDS measurement, and anything else needed to complete the data set later offline. So here you have the raw results, the phase map overlapped with the pattern quality map showing the distribution of magnetite. And everything else you will see from now on are results that have been offered by applying the advanced phase ID and subsequent re-indexing after finding a new phase and so on. So one example, instead of use the advanced phase ID offline, instead of going with the beam, so acquiring a spectrum and a pattern from a particular particle in the sample, you just move with the cursor in the map and select one spot, and immediately you will have access to the spectrum and pattern corresponding to that spot in, and you will apply then the advanced phase ID. And for example, here we found that for this phase present in this map was ilmenite, and after finding a new phase and inserting it in the phase list, user can re-index the map, and for these two phases and the whole map of 150,000 points, it approximately 50 seconds to obtain this. It now shows the distribution of magnetite in yellow and ilmenite in green. And repeating the procedure, we, for example, see that there was also pyrrhotite present in this sample in the data set. Of course, the procedure can continue until you find all the phases. What I have to specify is that is not a must to index after finding every new phase. You can, of course, you can apply phase ID, find a new phase, and then go and select another point in the map, and then actually, if you see that it had a different groove in the BSE image as compared to the one you identified before. And before continuing with this, at this point, I would like to pass the word to my colleague Lori, because as a material scientist, I rarely used to work with samples containing more than 3, 4, or 5 phases. So at this point, I will leave Lori to present you to take the microphone and present the rest of the results.
Thank you, Daniel. You hear me? Okay, good. So next step. So we can see that we have found 4 more phases. And so you can see such tabular clinopyroxenes in this igneous rock and some accessory quartz. And as you can see, we are still missing a lot of phases, and that's the complexity of most of rocks in general. It's like we have a lot of phases present in the rock, and plenty of those phases show similar phase contrast, because so as you could see in the black scattered image. So apply again advanced phase ID, and we find all the different phases. So in this map, we've identified 13 phases. So you see the clays in the light blue, and so part of probably the primary magnetic in rock like diorite, and some product of the alteration in dark blue is the homeland and Ansible. And as you can see, there are some dark areas that are non-indexed, and these are natural holes and cracks in the rocks. And there's one specific area here, so that we find and zoom in. This is a phase which is actually giving a very poor diffraction. So this is a chlorine chlor, it's a chloride, and so this is alteration of the W Ansible, and like we could get some patterns out of this semi-diffuse phase and identify it, so using advanced phase ID as clinochlor, so a chloride from hydrothermal mechanism deformation. The final reindex map, we've shown the orientation distribution along the x-axis. You can see so this map was reindexed at a speed of 1500 points per second, which is in fact within 8 minutes. So this last map was indexed 8 minutes. Once again, what we're showing are the raw data. There is no data cleaning done. The zero solution is about 12%, and so within the zero solution, you have the holes and cracks, fractures from this natural rock, and also some due to the clinochlor semi-amorphous phase. And I would like to emphasize on the quality of the data, because what we're showing here is the solutions using at least 7 bands, 7 detected bands, and you can see there is no misindexing, and the heat rate is really high. And also, thanks to the advanced phase ID, the user spent an hour loading the soil to launching the measurement. So to summarize the advanced phase ID method, so it's a search engine that is using it's a fast and interactive phase search engine using so unlimited number of selectable elements, and you can also use any phase data, phase database, both commercial and user database, and it offers different ways to select the elements. Its advanced phase ID uses a detection which can be automatic or interactive. So you have, like Daniel presented earlier, the automatic band detection, smart band detection, or manual band detection for a full call. And it has a fast indexing. It uses using a fast indexing algorithm, so you can find the solution fit. For instance, in between thousands of solutions, it will take less than a minute, and the results will be sorted based on the indexing quality. And to summarize now, so crystalline way to handle the data combined with the advanced phase ID and the ultra-fast offline reindexing allow you to acquire both simultaneously EBSD and EDS data without the need of knowing all the present phases, and you can complete and or correct your data set by using a very fast offline reindexing and offline phase ID. And the aim, of course, is to improve the efficiency for the user and CM time, and provide better data quality, because, for instance, you don't know the phases, or even if you know the phase but not selecting the best fit, then it might affect the heat rate and, of course, angular resolution. So advanced phase ID is a very powerful tool to characterize, especially to characterize polyphase materials, and it's designed to be used by both expert and newbies users. So thank you for your attention, and now I'll go back to Stefan.
Yes, so yeah, thank you very much to Laurie and Danielle for their presentation. And so now we have time for the Q&A session. We have received a number of questions, and you can still continue to plug in questions on the right-hand side of your screen. We will try and answer as many as possible. Okay, so now for the first question. So we have here, how much time can be saved by using the advanced phase ID over the conventional method?
Yes, if I start with this. Yeah, the answer, of course, it depends. It depends on many things, and the most important, I would say, is the number of phases you have in your sample. Also, it depends on how much you know about that sample, because, for instance, while it is clear that the number of phases present will affect the time you spend at the SEM, for example, if you don't know everything about the sample, or very little, you might launch a measurement without knowing that you have some second phase particle precipitates or some, like in this mineral, the quartz was present in a very small fraction, with just a few grains were present in there. And 1 second, if I may go back to the
15. Next slide.
Yes. 11. So here, you see that the quartz is present in just a few grains. Also, apatite. Sorry, so this was quartz in red, and apatite, this dark magenta. If we didn't, or if the user doesn't know about the presence of these phases, it may launch the measurement and then actually realize at the end of the measurement that it missed a few phases, and then of course that means a lot of time lost, because you'll have to go back to the SEM, identify them what they are, and then launch the measurement again, the final measurement. So how much time you can save? Yeah, it can be from a few hours to a day or two.
Okay, thank you, Dan. Next question. What size will a file containing EBSD and EDS data have?
Yeah, I'll take that one. And, yeah, the size will depend on what you save. For example, in this, maybe one of the questions you might have in mind right now would be, will I be forced to save the patterns all the time? If I want to do phase ID, it's not necessary. You can just save the position of the detected bands in the patterns, and it would mean an enormous decrease in file size. And by enormous, I mean, let's say, this map was with EDS and EBSD patterns. That particular resolution I showed you, 160 by 120 pixels, 12 gigabytes. Then that is a lot of space. But if you don't keep the patterns, that will go down to around 600 megabytes. So it's a very, very big change in size. And now, of course, if you want to keep the patterns, you can keep the patterns. You basically don't need the patterns, but maybe to be sure when you do the phase ID that the solution you find, the phase you find really fits to the pattern, but it's not a must. You can also use the detected bands, because you always know if you see a solution found with 11 or 10 or 12 bands, it's a very accurate solution. You don't necessarily need to have the pattern as a confirmation on the background. If you see a solution found with 5 or 6 or 7 bands, then it might be questionable. So yes, the file size can depend on a lot. It depends a lot on based on what the user chooses to save.
And also, it won't be a problem for the software to handle large files. So it's also designed to handle this very large map size. And maybe some mineralogists or geologists would like to save the patterns when they have poor patterns or phases that are very dense and some are very light. It's very difficult to prepare the sample, and so you have to work with poor patterns mixed with very nice ones. So of course you can, in this case, save them. Maybe you will need them, but usually, band detection, the detected bands are usually enough.
Yeah.
Both choice.
You can at least save them temporarily until you complete the map, and then just keep the map with only the results, the phase information and the orientation information, and then throw away the patterns.
Exactly.
Okay, so question number 3. Can I import my old data acquired with another system, and can I export the data acquired with the Bruker system in a format compatible with other systems?
The answer is yes. The data can be imported. The Bruker software allows you to save data in a text format, which is compatible with the 2 other main EBSD systems, existing systems, and that will allow you to it can export the data in that format, but you can also import the data in that format, which means you can load EBSD data sets acquired with the other EBSD systems. So what will not be possible is to import data sets containing EBSD and EDS information. This is due to differences in the way, let's say, we don't have yet a standardized mode of standardized file type saving the data, combined EBSD EDS data. Yeah. Then to export the data, as I said, we can export the data from the Bruker system in a format that will be compatible with the other EBSD systems.
Okay, thank you. Next question. What is the typical resolution mode used for acquiring this type of data, and maximum corresponding speed achievable in this mode?
So in this example, we were using a 10 by 10 binning, which is, if I go back to the slide, 160 by, sorry, which
sorry,
something like that. New, I don't know.
Higher.
Sorry. The first one. Yes, so 160 by 120 pixels, and so this was acquired with the high resolution detector. I'm using it's 10 by 10 binning, and as you can see, it's doing an amazing job even on minerals. So both here phases have low and high symmetry, and so it's compatible with the quality of data and speed. Yeah, maybe Daniel would like to speak in more material scientist in more methods.
Yeah, I would say
quite typical.
I would say for material scientists would be a much easier job. We are spoiled to work with materials giving much better diffraction signal, or most of materials in material science or samples in material science give much better diffraction signal than silicates, for example, for geologists or mineralogists. So the point here is you can see the results in this presentation today. They have been acquired with a panel resolution mode, which is not too high, but still the quality of data is pretty good. And then, of course, one uses the EBSD detectors, both the high speed or the high resolution detector, in a higher resolution mode, but that of course will affect the speed at which you acquire the data. And if the speed is not an important factor for you, then there is no problem with that. The advantage when using a higher binning or a lower pattern resolution is that you get much more signal, and then you will have lower noise patterns at decent speed, and then you can acquire very large maps in a reasonable amount of time.
And that's a very good point. If you work with carbonates, like as you can see here, there are plenty of phases, and so it's quite complex, and it's possible with 10x10 binning. So by using a 10x10 binning on carbonates, then we'll have much faster indexing, and then we can save the patterns instead of burn down the all in the mineral while we are acquiring at very low speed. So it's very helpful. And also there is quite impressive number of different offered binning possibility.
Yes, yeah. Well, at least for the high resolution detector, which is strongly recommended for mineralogical applications, the detector in native resolution acquires images in 1600 by 1200 pixels, and from that you can do 2x2, 4x4, 5x5, 8x8, 10x10, 16x16, and 20x20 binning.
Yeah, so it's really a lot of choices. So we have time for one final question, and this is: what is the smart band detection?
The smart band detection, is a option that we just we inserted in the software. It's with the advanced phase ID. In the future will be used in other parts of the software too. And it is actually the user automatically looks into the data set and takes the band detection results around the pixel in code, and it's kind of doing an average, and that allows, let's say, or minimizes the risk of having 1-2 bands slightly detected slightly off by doing this kind of averaging. So this is what the smart band detection is. It's doing a kind of averaging of pixels around the pixel we are looking at.
Mm-hmm. Thank you. So I special request one very last question.
Yes.
And our viewer wants to know the maximum resolution of the phase ID, for example, referring to particle size.
Yes. That's actually a very good question, because every I showed the integration between the EBSD and EDS, or I gave a talk, I would say maybe all the time I got questions saying, yes, but the resolution, spatial resolution of the EDS technique is pretty different compared to the one of the EBSD. And that's very true, especially when you do EBSD at 20 kV, actually voltage on silicates in this particular case. But so that, theoretically, or let's say in principle, would be a big issue, and would decrease the resolution of particles you could identify using this method. What is actually, well, in reality, it's not that big of a problem, because look when the, let's say, the quantification, and not only quantification, when the elements are detected from a spectrum before doing the phase search, the user interacts with it, which the user can immediately go next to the particle and see what the matrix is made of. So in the matrix iron and oxygen, and then you have a very small particle which contains some elements, but also iron and oxygen. Then when you do the phase search using the search engine, you may try many possibilities. You can try either to remove iron from the matrix or iron and oxygen as information given by the matrix, and also search based on the other elements. So for the moment, it needs the system. It needs reaction from the user, and especially in these particular cases where the particles or grains we are looking at are so small that they are maybe smaller than the resolution of the EDS technique, then definitely the user needs to interact and say, okay, that element, I know it comes from the matrix, is not present in this particle or grain. And in that particular case, the resolution would be the EBSD resolution, because we will need, the idea is done basically based on the pattern and on the EDS information. The EDS information is only helping us to narrow down the candidate phases from 160,000 phase files. So in that particular case, we will have the resolution of EBSD, which would be, for example, for silicates, maybe 100 nanometers. Field emission gun, good field emission gun.
Okay, so I want to thank everybody for attending today, and once again a special thanks to our presenters, Lori Palas and Daniel Warren, for their excellent work. As a reminder to you, this event has been recorded and will be available for viewing or download from tomorrow onwards. Thank you again for being with us. We hope this webinar was informative for you, and we look forward to your presence at one of our following events. Goodbye. Have a nice day or evening wherever you are.